once you access your browser, whichever browser you're using, and then you go to yaaka.cc/you're welcome. This from here up to here, okay? You can always see this course. You can search for it, Senior 2 Chemistry. It will be looking like this. Most of my courses, including biology, they have this picture here, this type of picture, the yellowish thing here with these big words. So you always easily see those courses. So subscribe to this course and just press the button here, start course, okay?
Yes.
Yeah. So after doing that, you'll see the units that are contained by going here where there is the word curriculum. Okay.
Yes.
So these are the units you have to cover for the whole year. When you're done, you can always talk about the others. But for now, you have all these units. Introduction to oxygen, rusting, oxides, water, hardness of water, hydrogen, atomic structure, isotopes, the periodic table, acids, bases, and indicators, salts, effects of electricity on substances. So those are the units we have. Now here is the deal, okay? Some of these units you might be very conversant with them. You know that you might be knowing them very well. Maybe you've covered at your school, and maybe you have a problem with, let's say, isotopes and isotopy. You can always let me know and say, teacher, I've seen this unit, isotopes and isotopy. I would love us to cover it before we cover anything else. We can always do that, okay? Or if you say, teacher, for me, I'll find problems with acids, bases, and indicators. Let's cover that first. I'll always adjust, and then we cover that. So it is all about you. Whatever you want to cover, we shall cover. All these units have assignments and activities that you can always be doing. So just ensure to go through, find the unit that you love to cover, we shall cover it. Or if you want just to continue chronologically from this one to this one to this one, we can do that too. For the last 4 weeks, we have been covering oxides. We covered the oxygen and oxides, okay?
Yes. Yes.
So if you have any other unit you want us to cover, we can always cover it. Now, when I give you assignments or activities that are not in this system, the way to submit them, just go here in messages, yeah? When you go to messages, you can create a new message, okay? You say create new message, you come here. When you press on this button, create new message, it will bring you here. Then search for my name, Teacher Solomon, just say Solomon, don't put teacher, you will not get anything. Solomon, see, it will bring me here, the one that is capital. You press on it, okay. And then you type your message, okay, here. Let's say, for example, you can say, teacher, here is the assignment for, then you can put the topic or whatever you named it. After typing that, you come here on the attachments, okay? If you have a picture, you can attach a picture. If you made a video, you can attach a video. If you made any other form, or maybe a PowerPoint, a PDF, a Word document, just go to this pin here. Do you see it?
Yes.
You press on it, it will take you to where you stored your assignment. Then you can attach it. Sometimes it disturbs, like right there. But I'm sure you can always do it. Yeah. Okay. Yeah. So you can do that and then attach the assignment, then send it. I'll always receive it. These are some of the assignments I've received. These are actually my own that I did, and then, but you can always attach yours and then send them. Okay, or if you want to just send me a message that, teacher, there is a problem with a certain assignment, or a certain problem with the unit, you can always type a message, I'll see it. Okay, we're here. Yeah, so these are the units right there. And if I have any comments, I can always put them for you there. You should explore this interface to see everything that you need to do. If you have questions, you can always ask. You should not worry that you'll press a wrong button and then delete everything. You can't delete anything here. So you should explore, press all these buttons and find out what is in here. Okay?
Yes.
And if you get questions, you can always ask. All right.
Yes.
So that's what I wanted to share with you about this. So then the next thing is for us to go through what we have been covering for the last 4 weeks, which is a unit, which is right. Let's see. Where it is. Okay, it's right here. So this is the unit we have been covering, oxides. All the notes that I sent you, I had already uploaded them here. So you can always access these notes now. You don't need to wait for me to send you PowerPoints or anything. You have these notes here. You can always go through, and if you want to copy them, feel free. If you want to summarize them, feel free to summarize them. Just do whatever you want. These are now yours. You've subscribed. You have access, full access, okay?
Yes.
So in the beginning, we looked at the types of oxides, the basic oxides, and then we looked at some of the reactions of these basic oxides. And there's a video here. I played it so that we can be able to watch it. Let me see if internet won't disturb. We can watch it. Let me first share my sound so that you can hear it well. Okay, so here is a reminder on basic oxides.
The basic oxide. Metal oxide.
Can you hear it very well?
Yes.
You can see and hear, right?
Yes.
Okay, let's play it.
Oxides are called basic oxides. They have a basic effect on litmus papers. For example, magnesium oxide. Burning the magnesium ribbon producing magnesium oxide. Magnesium oxide is a powder with the white color. From the previous, we conclude that magnesium oxide is a basic oxide that changes the color of red litmus paper into blue, while it has no effect on the blue litmus paper.
Okay, so that's it. That is magnesium oxide, one of the best examples for basic oxides. Okay.
Yes.
So okay, as you can see, basic oxides, what is one of their properties? What have you discovered?
Change blue litmus. They change the color of red litmus paper to blue, and they have no effect on blue litmus paper.
That is very correct. So that is the characteristic of basic oxides. Okay, good job. And then we looked at the acidic oxides. So for these ones, let's watch this video and see what they really are. So for these acidic oxides, as the video loads, for them, they are like the opposite of the basic oxides.
The oxides of the last two elements, that is phosphorus 5 oxide, sulfur 6 last two elements, that is.
Okay, let me pause it and put full screen so you can see well.
Oxides of the last two elements, that is phosphorus 5 oxide, sulfur 6 oxide, and sulfur 4 oxide, are all acidic oxides. This means that they react with water to produce hydrogen ions. A solution containing an excess of hydrogen ions is called an acidic solution, and the reaction products of phosphorus and sulfur oxides with water are acids. Such solutions change the color of universal indicator paper or litmus paper to red. Let us study the mechanism for the hydrolysis of sulfur 4 oxide. The lone electron pair on the oxygen atom in the water molecule is attracted to the unoccupied d orbital in the sulfur atom. As a result, a coordinate bond forms between oxygen and sulfur. At the same time, a hydrogen ion separates from the adduct, causing the medium to become acidified. Chlorine 7 oxide has the strongest acidic character among the oxides of period 3 elements. The reaction between this compound and water leads to the formation of chloric 7 acid, one of the strongest acids known.
Okay, so the key component here, besides the details don't really matter about the d orbitals and all that. Those ones will matter when you take chemistry in senior 6 or 5. But for now, what you have to know is that in acidic oxides, for them, they form, when they dissolve in water, they form acidic solutions. And acidic solutions are those that form hydrogen ions in solution. So for example, when carbon dioxide is dissolved in water, it forms carbonic acid. You see, carbonic acid contains hydrogen ions and carbonate ions, okay, when it is in solution. So these hydrogen ions are very, very key in us naming an acid, whether it is acidic or not. I mean, naming a gas, whether it's acidic or not, okay? So when a gas can produce these ions in solution, once dissolved in water, then we can call that an acidic oxide, right? So yes, so all acidic oxides can produce hydrogen ions in solution, like we have seen in the video, okay? The examples are here. Carbon dioxide, sulfur trioxide, and nitrogen dioxide. Okay, there are others that you can always research and find out what they are, like phosphorus, pentoxide, and others. So these are the non-acidic oxides. And we have seen what they can do, producing hydrogen ions when they react in water. Can you tell me what effect acidic oxides have on litmus paper?
They change blue litmus paper to red and leave, and they have no effect on red litmus paper.
Very good. They change blue litmus to red and have no effect on red litmus paper. Yes, that is very, very correct. Let's look at the neutral oxides and see for them what is special about them. Okay, this one has no words, so I'll read for you so that you can concentrate on seeing what is taking place. Neutral oxides are neither acidic nor basic. They are neutral towards litmus paper, water, for example. Nitrous oxide or laughing gas is a neutral oxide, has no action on litmus. Nitric oxide is also a neutral oxide, and its color is right there to the left. However, when it combines with atmospheric oxygen, an acidic oxide, nitrogen dioxide, is obtained. The brown one that you can see over there. Carbon monoxide is highly toxic among neutral oxides, and it's slightly soluble in water. And see it dissolves to form that solution. Carbon dioxide absorbed by sodium hydroxide under pressure, forming sodium bicarbonate. Carbon monoxide burns with a pale blue flame, forming carbon dioxide, which is an acidic oxide. They are using it right there to burn, and that is the reaction that takes place. Okay. So that is the neutral oxides. For the neutral oxides, we have seen that they're very, very good at not reacting with, for example, with water to form acidic solutions like we saw with acidic oxides. For them, they are neutral to litmus solutions or litmus paper. Yeah. Okay, so most of them, the examples we have seen: carbon dioxide, nitrogen monoxide, dinitrogen oxide, which we also call laughing gas, then water, which is hydrogen oxide. The reason why we call dinitrogen oxide laughing gas is because this gas stimulates a certain gland in your body to produce a hormone that makes you feel a certain type of euphoria or a certain type of happiness. Okay, it's mostly used when they are if you go to a dentist and they put a gas on you, a gas mask on you to perform that anesthetics to kind of relieve pain. It is dinitrogen oxide. Okay, It is nitrogen oxide. It is used by dentists most times. It makes you feel so good, like everything is good. Eh? You start laughing out of nowhere. The people who discovered it on the village, I don't know what they were doing. I think they were probably making a certain alcohol or something, and the gas was produced, or they combined yeast and something, making cheese. I'm not sure what they were making. Then they started laughing. They didn't know what was making them to laugh. So they named it the laughing gas when they discovered it was the gas. So that is dinitrogen oxide. It's one of the neutral oxides we have. The other types of oxides we have are amphoteric.
Both acidic.
Yes, amphoteric oxides. Examples of these are aluminium oxide, lead 2 oxide, and zinc oxide.
Yes.
Below are their reactions. When zinc reacts with sulfuric acid, you form a zinc sulfate and water. When aluminium oxide reacts with HCl, you form aluminium chloride and water. Then when they react with other alkalis, for example, zinc oxide reacts with sodium hydroxide to form a complex. This is sodium zincate. They just form complexes when they react with these alkalis like sodium hydroxide. When aluminium reacts also, aluminium oxide, when it reacts with sodium hydroxide, you form another type of complex, which is right here, sodium aluminate. This is how we write it. Yeah. So those are the reactions for the amphoteric oxides. What is key about amphoteric oxides? So far, what have you seen, which is different from all other oxides?
They have both acidic and basic properties.
So yeah, they sort of react with both acids and alkalines. Okay. All the rest hardly do that. So for them, that is their key component. They can react with both acids and alkalines.
Alkalis.
Yeah. So that's how special they are.
Yeah.
Let's see this video and see what they tell us more about amphoteric oxides.
Amphoteric oxide. Metal oxides which react with acid as well as base are called amphoteric oxide. Example, aluminum oxide, zinc oxide. Aluminum oxide reacts with sodium hydroxide to form sodium aluminate and water. Aluminum oxide reacts with hydrochloric acid to form aluminum chloride and water. Zinc oxide reacts with hydrochloric acid to form zinc chloride and water. Zinc oxide reacts with sulfuric acid to form zinc sulfate and water. Zinc oxide reacts with potassium hydroxide to form potassium zincate and water. Thank you for watching the video.
So that was as simple as that, okay? The very things that we have talked about, their reactions. The special thing about them is that they can react with both acids and alkalis. That's the only special thing about amphoteric oxides.
Yes.
Yeah. So the other oxide that we have are the peroxides. So yes, the peroxides contain twice as much oxygen as is contained in normal oxides. So for these ones, they are formed by those atoms that can attract a lot of oxygen atoms. For example, we have sodium peroxide and hydrogen peroxide. Sodium is capable of attracting more oxygen atoms than normal or than other elements. This is why we can form sodium peroxide. Hydrogen the same, it's capable of attracting many oxide atoms. Okay, so that as a result it forms the peroxide.
Yes.
This hydrogen peroxide, if you have ever gotten a wound and went to the nurse and they put on that wound a certain liquid that formed a lot of froth or bubbles, a lot of bubbles, and it's painful, that was hydrogen peroxide. Okay, that's
Yes.
one of the. It is very, very antiseptic, or it kills bacteria around surfaces. So people use it for that. When they don't put iodine on you, they'll put hydrogen peroxide. Have you ever encountered that?
Yes.
Okay, so that was hydrogen peroxide right there. Let's look at, let's see what they have to say about this in this video about peroxides, if there is anything new that we can learn.
A peroxide is a compound containing an oxygen-oxygen single bond, or the peroxide anion, O2-2. The OO group is called the peroxide group or peroxo group. In contrast to oxide ions, the oxygen atoms in the peroxide ion have an oxidation state of -1. The simplest stable peroxide is hydrogen peroxide. Superoxides, dioxygenals, ozones and ozonins are considered separately. Peroxide compounds can be roughly classified into organic and inorganic. Whereas the inorganic peroxides have an ionic, salt-like character, the organic peroxides are dominated by the covalent bonds. The oxygen-oxygen chemical bond of peroxide is unstable and easily split into reactive radicals via homolytic cleavage. For this reason, peroxides are found in nature only in small quantities, in water, atmosphere, plants, and animals. Peroxide ion formation has recently been highlighted as one of the main mechanisms by which oxides accommodate excess oxygen in ionic crystals and may have a large impact on a range of industrial applications including solid oxide fuel cells. Peroxides have a bleaching effect on organic substances and therefore are added to some detergents and hair colorants. Other large-scale applications include medicine and chemical industry, where peroxides are used in various synthesis reactions or occur as intermediate products. With an annual production of over 2 million tons, hydrogen peroxide is the most economically important peroxide. Many peroxides are unstable and hazardous substances. They cannot be stored and therefore are synthesized in situ and used immediately.
Okay, so those are the peroxides. The information in there was all about the bonding in the peroxides. These two oxygens have a bond together, the oxygen to oxygen bond. And they told us that it is very unstable. Therefore, in the environment, you'll hardly find many traces of these peroxides because the environment makes sure that this bond is broken. So that, for example, when this bond is broken in the sodium peroxide, you only remain with sodium oxide. So normally we find sodium oxide, not sodium peroxide, because of that matter. Even in the hydrogen peroxide, we normally find just water, the hydrogen oxide, because the oxygen to oxygen bond easily breaks. It's not that strong. Yeah. And then also like we talked about the use of hydrogen peroxide, it is one of the most important oxides because we use it in medicine. Like I told you about injuries.
Yes.
So those are the peroxides. Okay. The last type of oxide we can look at is the mixed oxides. And these are oxides that react like a mixture of two simpler oxides. For example, lead tetraoxide and iron tetraoxide. Yeah, so those are sort of complex oxides, or they are mixed oxides. They react like they are two different entities. Let's see if they have given us any reactions here that we can use as an example. This one is going to be very, very short. So it's a simple definition of mixed oxides. Let's see the meaning.
Mixed oxide. Mixed oxide.
I don't know why I included these two.
Any
mixture of oxides, metal specifically, blend of plutonium and uranium oxides that is used as mocked fuel in nuclear reactors. That is not that helpful, but this is another example of a mixed oxide that works as fuel. But anyway, the key part here is that these oxides are sort of complexes, okay? They are complex in such a way that it looks like they are two oxides that have been mixed together, okay?
Yes.
That's the key part on mixed oxides. So last week, we also looked at the reactivity series. You were around last week, not so?
Yes.
Okay, so we looked at this reactivity series. We saw, I gave you an activity of finding an acronym for the reactivity series, how they are arranged. I don't know if you did that. Only a few people did. So if you find time, make your own acronym to remember this arrangement, that potassium is the most reactive and the least reactive is gold. Okay?
Yes. Yes, I have the
Find time.
acronym.
Oh, you have?
Yes.
Do you remember it?
Yes.
You tell me.
Please send cats, monkeys, and zebras in lovely happy cages made of silver and gold.
Ah, nice. That's a good one. That's a good one. So well done. Yeah. Okay, so let me leave this video to load up and then we can watch it later about reactivity series. Let me first leave it there to load up a little bit, then we'll talk simply about reactions between metals and nonmetals.
Yes.
So this is a reaction between an oxide and a metal. For example, this is an ion displacement reaction. Magnesium reacts with copper oxide from copper and magnesium oxide. When you look at this reaction, between copper and magnesium, which one is higher in the reactivity series?
Magnesium.
Magnesium is higher in reactivity series. That's true. So therefore, magnesium is capable of displacing copper away from this oxygen. Okay. So therefore, when we react, we form the magnesium takes the oxygen because it is stronger than, it is more reactive than copper, and then copper remains lonely with just copper metal. Okay, so the reaction here is displacement because of the difference in the reactivity series. So yeah, that shows a good example on how to apply the knowledge of reactivity series. Yes. The other one we can look at is here, carbon and copper. Still, carbon is more reactive than copper, so it will displace the copper away from the oxygen, and then you remain with the copper solid, and carbon dioxide will be formed.
Yes.
Here we see magnesium is more reactive than carbon, of course. So magnesium will displace the carbon away from this oxygen, and then to take up the oxygen for magnesium oxide, and then carbon will be displaced off. Okay. So let's watch the other video, then I'll tell you about those assignments. Let's watch this video. This is about the reactivity series. So let's see what we have here.
In this video, we're going to learn about the electrochemical series, what it is and how it is used. In the video Measures of Electricity, we found out that different combinations of metals produce different voltages, and this depends on how strongly the metal could force its electrons to move across a cell. The electrochemical series is a list of metals and other substances arranged in rank order of how easily the atoms may lose electrons. The further apart the metals are in the electrochemical series, the higher the voltage is produced across the cell. Electrons flow along the wire from the metal higher in the electrochemical series to the metal lower down. The electrode potentials are arranged in the substance's ability to donate its electrons, that is, how easily they are oxidized. All of the values are measured in volts. What do you notice about hydrogen's voltage, and what is the significance of this? Pause the video and continue when you are ready. The answer is that hydrogen has an electrode potential of 0 volts. The significance of this is that it acts as a reference. All other electrode potentials are measured against this value. It's a bit like the heights of a mountain, which are relative to the sea level. The sea level is given a height of 0 meters. Using the electrochemical series, can you predict the direction that the electrons will travel towards for the following pairs of metals? The electrons always move from the metal with the more negative electrode potential to the more positive electrode potential. Pause the video and continue when ready. For A, the answer is the electrons move from potassium to hydrogen. For B, the answer is the electrons move from zinc to copper. And for C, the answer is the electrons move from lead to mercury. You can also use the electrochemical series to predict a displacement reaction when a metal from the electrochemical series is mixed with ions of a metal lower down in the series. The atoms of the more reactive metal push their electrons onto ions of the less reactive metal. Let's consider what happens when an ion now is placed in a solution of copper sulfate. The higher up metal in the electrochemical series is the one that always displaces the ions of the lower down metal. Metals lower down in the series cannot displace more reactive metals from their solution. You can use this idea to predict whether a displacement reaction will occur. Here's a challenge. Can you explain why the ion now formed a copper coating when it was placed in a solution of copper sulfate? Pause, think, and continue when ready. The correct answer is that the ion is higher in the electrochemical series, so it gave away its electrons to the less reactive copper-2 ions in solution. The ion is oxidized as shown in the equation. The copper is less reactive, so its copper-2 plus ions are forced to accept these electrons. This is called reduction. As a result, copper metal is produced and coats the now, as shown in the reaction. These two processes happen simultaneously in something called a redox reaction. In summary, the electrochemical series contains electrode potentials measured in volts, which are compared to hydrogen. The greater the difference between the two substances in the electrochemical series, the more readily the electrons move from the more reactive metal, i.e. the more negative value, to the less reactive metal, i.e. the more positive value.
Okay, so that's it with the electrochemical series. What have you picked out from this video? What are the key things that you've picked out that stood out for you?
That the electrons, they move from an element which is higher to the one which is lower in the reactivity series.
That is correct. Good job. So yeah, that is the most important thing in this video actually, that how we arrange these elements is how easily an element can donate its electrons. So therefore, potassium can easily lose its electrons than iron or lead, or even the one that is next to it, sodium. Okay, so electrons, the way those battery cells that they showed in the video are the way that we used to measure this reactivity. Okay, with the base being which element did we base on, which has zero electrode potential? Do you remember? The element that has, yes, so hydrogen is always our base. Okay, it has zero electrode potential, meaning for it, it can hardly lose or gain its electrons. It's very, very hard. For it to do that, you have to have so many other conditions present. Okay, so we used that as our base to measure all electrode potentials of each of these metals. And what we find out is that potassium has the lowest, meaning it can react more than the rest. Okay, it has the least, the most negative. So that's the reason for the battery cells that you saw. They were showing us how the scientists came up with this series. It's all about measuring the electrode potentials of each metal. Okay?
Yes.
Yeah, so that's it. That's electrochemical series. That is this unit about oxides. So the entire unit, we have gone through it. We had already gone through it for the last 4 weeks or 3 weeks. So therefore, now you have all the knowledge you need. Access it anytime you want to go through these videos and the content. And then what I want you to do is start attempting the assignment. As you can see, I have an assignment for you here. Okay. This one is attached. Go to your interface. You'll see it there when you open the unit. Yeah, to be down. You scroll down, open it, download it, do it, and then submit. Okay. You have 1 week and 3 days. Those are 10 days for you to do it. But you can do it in less. Yeah, it doesn't matter. So whenever you're done, submit it. I'll see. If you have questions about it, you can ask me anytime you want. Just text me on WhatsApp and I'll respond to you. Okay?
Okay. Yes.
Well done for today. Good job. Do you have any questions for me?
No.
Okay. Good job. Enjoy doing that assignment. Make sure you ask questions if you have any. That's it for today. I will see you next week. Bye-bye.
Thank you, Teacher Solomon.
You're welcome.
Thank you, Shania, for your attention.
You're welcome.
Have a nice time.